Let us start with a work energy theorem, which is a crux of this chapter, which is a, we can say, heart of this chapter. But work energy theorem, this totally spread on this work power energy chapter. Okay, so in this, what happens? There is a relation between work and kinetic energy, especially. So there are two types of energy: mechanical energies, potential as well as kinetic. But here, this equation gives a relationship between work on left hand side and yes, change in kinetic energy on the right hand side. So left hand side is a work done by net force, or we can say net work done, not a work done of single particle, etc. This is a single force, etc. Work done, net work done is equal to change in kinetic energy. But again, there is a mixing of kinetics and kinematics. Okay, displacement, final velocity, initial velocity are the kinematical data. We have to deal with carefully about these kinematical data, and force is a kinetics data. So work done, net work done is equal to change in kinetic energy of the body, and how they are related. So let us begin with the some basic concept of energy, because yes, we have to study conservation of mechanical energy, in which potential energy and kinetic energy we have to study in detail. But now, slightly begin with the energy and how work and kinetic energy related with each other, and yes, mathematical expression of this theorem, which is called work energy theorem or work energy principle in simple sense. So this equation is very useful instead of Newton's second law of motion. Remember, F is equal to mass into acceleration is a kinetics of the particle. Similarly, it is extension of that equation, or outcome of that derivation of that F equal to ma. You can derive in this way. So work done is change in kinetic energy is also a kinetic equation, special equation, and you can apply this equation to get a displacement, to get a velocity, either final or initial. And using this data you can calculate acceleration. Using this data you can calculate acceleration. So in Newton's second law of motion, acceleration, yes, acceleration we can calculate initially, and using that acceleration, velocity and displacement you can calculate. But in work energy theorem, remember, you have to calculate initially a displacement and velocity, and then you can calculate using the kinematical equations acceleration for the system. Okay, so let us begin with the energy and end with the work energy theorem expression and some sign conventions which are very important while solving a numericals. Okay, baga, let us begin with the energy. Energy is the capacity to do work. It may be a potential or yes, kinetic. And remember, work is a measure of energy transfer that occurs when an object is moved over a distance by an external force. बघा आता यासाठी एक थोडंसं प्रॅक्टिकल एक्झाम्पल आपण काही घेऊयात टू गेट द आयडिया ऑफ अबाउट अ कायनेटिक एनर्जी अँड देन मॅथमॅटिकल एक्सप्रेशन्स. बघा आता इथे तुम्हाला धनुष्य आणि बाण दिसतंय. तर बघा आता ह्या बाणला आपण कसं ताडून धरलंय आहे की नाही. सो रिमेंबर, in this situation it has some capacity to do work, and that capacity is nothing but called, बघा अशा केसमध्ये जेव्हा आपण असं बाणाला काय केलं, असं ताणलंय, आपण आता मारण्याच्या स्थितीमध्ये आहोत, अशा वेळी त्याच्याकडे एक एनर्जी असते, and that energy is nothing but you can call it potential energy. that is a potential. बघा आपण नॉर्मल लाईफमध्ये पण पोटेन्शियल याचा वर्डचा उपयोग करतो. कसा करतो की माझ्याकडे एवढं पोटेन्शियल आहे. इट मीन्स व्हॉट, माझ्याकडे 720 मार्क घ्यायचं पोटेन्शियल आहे. मीन्स व्हॉट, यू आर हॅव्हिंग अ एनर्जी फॉर फ्युचर, यू आर हॅव्हिंग अ समथिंग फॉर फ्युचर. सो इथं पण तसंच आहे, हे असं ताणून धरलं आहे म्हणजे याचा अर्थ काय आहे, इट हॅज एनर्जी फॉर फ्युचर. बघा एखादी स्प्रिंग आपण स्ट्रेच केली, सो इट हॅज अ यस पोटेन्शियल एनर्जी इन दॅट केस. जेव्हा आपण त्याला सोडू, इट कॅन डू सम वर्क, or it can also transform in other form of energy as per the law of energy, conservation of energy. So in this case what happens, बघा आता इथे बाण असा ताळून धरलाय म्हणजे याच्याकडे कुठली एनर्जी आहे, आत्ता लक्षात घ्या, याच्याकडे आहे पोटेन्शियल एनर्जी. सो इट हॅज अ पोटेन्शियल एनर्जी. बघा वन्स हे बाण आपण सोडून दिला की इट हॅज सम वेलॉसिटी, इट हॅज सम वेलॉसिटी. सो वेलॉसिटी आली की काय येतं मग, कायनेटिक एनर्जी. Okay, this kinetic energy is a half mv square, and this energy can do a some work. म्हणजे तो जर फोर्स अप्लाय करत असेल आणि बॉडीला तो डिस्प्लेस करत असेल, सो इट गिव्स अ वर्क. म्हणजे इथं काय सिक्वेन्स आहे, पोटेन्शियल एनर्जी स्टोर्ड होती, आपण त्याला रिलीज केली, we gain a kinetic energy which can do a work, which can do a work. So work is a measure of energy transfer that occurs when an object is moved over some distance by some external force F. And energy, it may be a potential or whatever. Kinetic is a capacity to do work. It has a potential to work, then it is called potential energy. If body moving actually with some velocity, if mass moving with some velocity, that gives a kinetic energy. So kinetic energy, potential energy is this mg into h. बघा, आपण आता पोटेन्शियल एनर्जीच्या जास्त खोलात जाणार नाही तिथे, बिकॉज आपल्याला शिकायचं कन्झर्वेशन ऑफ मेकॅनिकल एनर्जी. त्या केसमध्ये आपण ह्या दोन्ही एनर्जीला अजून डिटेलमध्ये डिस्कस करणार आहेत. पण आता या क्षणी आपला इम्पॉर्टंट एनर्जी आहे कायनेटिक एनर्जी, विच इज गिवन बाय हाफ mass v square. If mass moving with some velocity, yes, there is a kinetic energy. Remember, if you apply a work to add kinetic energy or to decrease its kinetic energy. So बघा, जे kinetic energy ॲड करण्यासाठी म्हणजे जेव्हा kinetic energy ॲड होते that work is positive, आणि जेव्हा kinetic energy रिमूव्ह होते किंवा लेस होते that work is negative. आपण ते बघूयात. So our sole purpose of this lecture is relation between work done and kinetic energy. पण बघा, हे अशा तऱ्हेने आपला विचार करता येते की potential energy it has already stored, then you can convert into kinetic energy and that may do a work. Or work and kinetic energy, remember, they are interchangeable terms. ते आपल्या subsequent lectures मध्ये कळत जाईल. Okay, so now moving to relation between work and kinetic energy, and then yes, work energy theorem. Okay, let us concentrate on kinetic energy. बघा, आपण काही प्रॅक्टिकल एक्झाम्पल बघूयात. जस्ट लाईक अ kinetic energy is nothing but energy possessed by a body by virtue of its motion. This is a popular definition of kinetic energy. That is, but when mass is moving with some velocity, that always has some kinetic energy. बघा, आता इथे एक्झाम्पल दिसतंय, हॅमर आहे, इथे एक नेल दिसतोय तुम्हाला. नेल म्हणजे खिळा किंवा पाईल म्हणता येईल त्याला, मोठा खिळा असेल तर. So that is nothing but example of this. Hammer had some velocity. Hammer had some velocity. With this velocity, it strikes on this top of the pile or hammer. काय होतं नंतर, हे याच्या आत जायला लागतं. Means there is some work. So remember, a moving hammer drives a nail into the wood or into the soil, we can say. Being in motion, it has some kinetic energy or ability to do work. Remember, it has some kinetic energy, means it is able to do work. It is able to do work on this particularly nail or pile. बघा, आपण आता एक एक्झाम्पल घेऊ, फास्ट मुव्हिंग ऑब्जेक्ट. सो दिस फास्ट मुव्हिंग ऑब्जेक्ट आहे. समजा इथे तुम्ही जर दगड ठेवला असेल या विंडो पेन जवळ, विंडो ह्या पॅन जवळ, तर काय होणार आहे? So there is no any breaking of this window glass and all things. But when you throw the ball with some velocity, so it possesses a kinetic energy. So moving object, a fast moving object can break a window glass, etc. So it has a kinetic energy and therefore it can do a work. Even though a bullet fired from a gun can do hole in the target because of its kinetic energy. So because it has a kinetic energy, so it can do a work. So kinetic energy of air is used to run a windmill also. बघा, windmill आपल्याला रोटेट होतं because of that. So yes, kinetic energy of the air, it has a velocity used to run the windmills, etc. So there are number of practical examples of kinetic energy. So which is used to run a water mill, which is used to run a turbine also. So these are the examples of kinetic energy. So बघा, इथे आपण पाहिलं potential energy is converted into kinetic energy and that able to do work. And in the same way, yes, if you apply a work, if you add a work, if you give a work, then there is a change in also kinetic energy. So that we have to study in again in some examples. बघा, चला इथे समजून घेऊ आपण what is the relation between work and what kinetic energy. बघा, आपण अगदी रँडमली एक्झाम्पल करूयात. बघा, हा बॉल आहे, दिस इज बॉल हिअर. सो इट इज ॲट रेस्ट कंडिशन इनिशियली. Okay, it is suppose at rest condition initially, means its velocity, initial velocity is 0, or we can get vi equal to 0, any notation. So it is 0 velocity. And if you add force to this, if you add force, so it displaced by this distance. Okay, displaced by this distance, that is suppose yes. So this force is applied here, means you are imparting, you are giving a work to this ball. So there is a gain in velocity which is greater than 0, or we can say this is V final greater than V initial. What happened here? Here kinetic energy, yes, increases. So such work is known as a positive work. Positive work when it increases a kinetic energy. Remember, when it increases a kinetic energy, the work is to be done on the ball, on the object, on the stone, etc., which increases the kinetic energy. That work is nothing but known as a, yes, positive work. So here positive work is given to this ball, so it gains a velocity. Similarly, if suppose it is moving with some velocity Vi and it is stopped by this resisting force, what happens? Yes, maybe it stops. Let us say it stops, Vf equal to 0. Maybe there is a decrease in velocity. So work applied by this force, resisting force, is, remember, a negative work. Why it is negative work? Because it decreases the kinetic energy. It decreases kinetic energy. Initially, it, yes, moving with some velocity Vi, which is greater than 0, and because of this resisting force, its velocity becomes 0. So this is called a negative work. So how these are work and kinetic is related. Okay, another example of this falling a ball. Okay, this is falling with, yes, suppose this velocity is 0 initially, so Vi is 0, but remember V final is greater than V initial. So there is a, yes, there is a what? Increase in kinetic energy. So such work is also positive work and done by this force mg. Okay, mg is, so displacement, this displacement is in this direction, mg is also acting towards the center of earth. So this also example of adding a kinetic energy, increasing in the kinetic energy. And if you consider this upward projection, so it has some velocity V initial, but at final, at maximum height, you know, its velocity becomes 0. So here kinetic energy decreases. So this work is nothing but known as a work. But force mg is there, but displacement is in this direction. So in all four cases, remember what is observation? There is a change in kinetic energy. Either it increases or decreases, that is another thing. So there is a change in kinetic energy. If there is a change in kinetic energy, then work is done. It may be a positive work done or negative work done. When velocity increases, kinetic energy increases, the work done is said a positive. And if velocity decreases, kinetic energy decreases, that work is said a negative work. But remain one example, daily example. बघा, एक हेवी बॉक्स आहे आणि तुम्हाला काय सांगितलंय की या हेवी बॉक्सला ढकला आणि इथे नेऊन ठेवा. पण विचार करा, इनिशियली इट was at rest, means initial velocity 0, and finally it again becomes at rest, means Vf equal to 0. Is there any change in kinetic energy? Yes, answer is there is no any change in the kinetic energy, because velocity is not increases or decreases here. Velocity constant, velocity Vi equal to 0, Vf equal to 0. So there is no gaining of kinetic energy or losing of kinetic energy. So बघा, आता या मुलाला आपण सांगितलं, हा मुलगा वाटत नाहीये, पण इमॅजिन करा हा मुलगा आहे आणि ढकललाय नाही बॉक्सला, हेवी बॉक्सला, पण तो पुन्हा रेस्टला आलाय. तर तो म्हणेल मी आता खूप काम केलोय, थकलोय. पण फिजिक्स म्हणेल यू आर डुईंग नथिंग वर्क. कारण वर्क डन कधी म्हणायचं? इफ देर इज अ चेंज इन कायनेटिक एनर्जी. ओके, आयदर इंक्रीजिंग और डिक्रीजिंग, इट इज डिपेंड अपॉन अ फॅक्ट. बट रिमेंबर, if there is a no change in kinetic energy, so no work done. So in this case, work done is 0 in physics. So according to physics, okay, according to you, it is I have done more work. आता मी खूप थकलोय, it's okay. But physics said yes, you are not doing any work. So according to physics, there is a no work. If there is a change in kinetic energy, there is a work, and that relation is given by work energy theorem. So let us move for the mathematical expression of work energy theorem. So these are the examples which relates work and kinetic energy. Okay, now some while potential energy not coming here, but this gives a solely relationship between work done and kinetic energy, because both are, yes, it is a dynamics part, kinetics part, or mixing of kinetics and kinematics. So let us express this equation. Let us prove mathematically work energy theorem. Okay, statement is what? A work done by all forces acting. Baga, all forces means what? All forces means work done by all forces means conservative forces, non-conservative forces, external forces, internal forces, etc. Work done by all forces, that is W net you can call it, of particle is equal to change in the kinetic energy. So mathematically you can write these words W net is equal to a change in kinetic energy, okay, initial to final, final to initial, etc. So mathematically also you can, yes, express like this, summation F into S. This is a real meaning. Summation F means all together forces, resultant of that forces in the direction of motion displacement. So this is a popular statement of work energy theorem. Okay, let us prove this. बघा आपण समजा इथे एक ब्लॉक, इथे एक बॉडी आहे, इट हॅज सम वेलॉसिटी, से इट u or vi, maybe a notation. So it travels to some distance, let us say distance s, or we can say displacement s. As a unidirectional you can say this all. Okay, if you apply force to displace this body, force F, and this gains a velocity vf, means there is an increase in, yes, kinetic energy, means work is done there. So it has some mass, okay, mass m. बघा आता आपण याला एक कायनेमॅटिकल इक्वेशन जे आपलं पॉप्युलर आहे ते आपण जर घेतलं तर v स्क्वेअर इज इक्वल टू u स्क्वेअर प्लस yes 2as, you know this equation. So v square minus u square is nothing but equal to 2as. But remember, as this body accelerate, there is a change in velocity, there is a body accelerate. So according to this Newton's second law of motion, force is equal to ma. So this is equal to force by a mass. So you can replace this u square 2 into f upon m into s. Okay, so what we get, f into s, f into s is remaining there. So that becomes v square minus u square, yes, divided by this mass, continue kara, this mass by 2. So this fs becoming now this 1 by 2, popularly this mass v square minus u square. Remember, this half m v square minus u square is a change in kinetic energy. So this fs is work done, and this will be a change in kinetic energy. If force is constant, is this case, okay, in this case what is this, force is constant. If force is constant, then you can get this expression, that is work done, net work done you must say, as in this case there is one force, but net work done is very important term. So W net becomes delta Ke, that is a change in kinetic energy. If force is variable, suppose if force is variable, then you have to do some mathematical operation, okay. So integration is there. So in that case W is equal to integration f into dx in that case, okay, f into dx. So f is ma dx, okay. So this gives us a mass is there, but yes, this is dv, v dv by dx. You can replace acceleration by v dv by dx, v dv by dx, and there is a, yes, term dx, and this gives us from, you can put limit from u to v, as this becomes u to v here, you can put here mv dv. So that gives us m as it is, but integration of this v dv by dx, okay. So that gives us a v square by 2, integration v square by 2, and if you put limit like this, a taken mass common in bracket v square by 2, that is u to v, initial and final velocity. So this is again a same story, 1 by 2 a mass, 1 by 2 a mass, v square minus u square, okay. This gives a work done. So work done becomes again change in kinetic energy, that is 1 by 2m v square minus u square, okay. By recalling why a is dv, v, how it becomes a equal to dv by dx. Okay, A equal to how replace? Maybe this question arises. A equal to dv upon dt. You know that. पण dv upon dt ला काय केलं आपण dx upon dx नी multiply and divide केलंय. मग काय होईल dx upon dt is a v, so remaining is dv upon dx, and therefore we can replace A as acceleration in this form v dv upon dx, and in this case this cancel out. That's why v dv is there. Integration of that v square upon 2. That gives us this formula again. So for variable force, this is आपण variable force ला अजून discuss करणार आहोत. At that time I will explain again this theorem. But remember here become W net equal to delta K, that is a change in kinetic energy all together. So we can conclude the work done by all forces, conservative, non-conservative, external, internal, etc. is always equal to change in kinetic energy. पण लक्षात घ्या इथला जो लेफ्ट हँड पार्ट आहे it also a mixing of kinetics and kinematics. The force is a kinetics quantity, displacement is a kinematical quantity, and delta K in that final velocity and initial velocity are they are kinematical quantity. So let us discuss about a sign convention, how to apply for different cases before going to conclude this lecture. ओके, दोन एक्झाम्पल बघूयात आपण. त्याच्यामध्ये हे वर्क एनर्जी थेरम आपला अप्लाय करता येईल, अँड व्हॉट आर द साइन कन्व्हेन्शन्स फॉर दॅट. ओके, सो ड्युरिंग वर्क आय हॅव एक्सप्लेन अबाउट अ साइन कन्व्हेन्शन्स. सो डिवाइड युअर forces in 3 categories. One is a applied force, second is a weight and weight component, and third one is a very good, frictional force or resisting force. If direction of applied force, okay, let us revise this. Direction of applied force, let us say P. If direction of applied force and displacement are in the same direction, okay, then remember work done is positive. If direction of applied force P or F say and displacement opposite to each other, in that case work done by such applied force is negative. Okay, negative. For weight component, okay, for weight means let us take mg. If body moving upward, so for mg work done taken negative, and if body moving downward, okay, work done taken positive. Okay, work done positive because it adds a kinetic energy in this case, and in previous case it reduces kinetic energy. And for any resisting force like a frictional force, okay, frictional force Fs or Fk, whatever, so work done is not Fs, Fk is always a negative. Okay, negative. So these are the conclusion of sign conventions. Let us apply this theorem totally. Say this body is moving with some velocity. Yes, initial velocity we can take u as a v, I suppose v as a vf, and there is some displacement. And if you consider forces on this block, that is force mg, okay, this is normal reaction R, and suppose there is a force P or F, and there is a frictional force, which is a Fk. Okay, so mu k into R. And if you want to apply work energy theorem for this whole system, तर डिस्प्लेसमेंट ऑफ द बॉडी आधी काय बघायचं, डिस्प्लेसमेंट काय, ह्या बॉडीची डिस्प्लेसमेंट कुठल्या डायरेक्शनमध्ये व्हायला लागली, दॅट इज व्हेरी इम्पॉर्टंट. सो डिस्प्लेसमेंट इज इन द राईट डायरेक्शन सपोज. ओके, सो डिस्प्लेसमेंट इज इन द राईट डायरेक्शन. सो वी हॅव टू अप्लाय लाईक दिस. अप्लाय W net. Remember, W net is equal to a change in kinetic energy. So W net is summation F into S is equal to change in kinetic energy. How many forces are parallel to motion? ह्या displacement ला कोणकोणते force parallel आहेत? This force P is there and this frictional force. Only these two forces you have to consider, because you know that work done by R, normal reaction, and work done by mg is 0, that we have studied in work separately. So here only interesting force are P and mu k. So what is P's category? Yes, applied force category. So this is applied force category. So direction of applied force rightward, displacement rightward. So you have to take like this P into S, and for frictional force remember it is always negative. So minus Fk into S is equal to half this mass final velocity square minus initial velocity square. So in this way you can apply work energy theorem for any a block or system of blocks, even though okay system of block ला आपण शिकूयात, पण आता आपण ब्लॉकचं बघूयात. This is how to apply a work energy theorem for yes block system. Now consider for this, suppose it has a mass, okay, it has a mass m, and suppose this is a displaced in this way. This is again having a initial velocity vi and final velocity vf. So let us draw free body diagram for this. बघा आपण आता हे x म्हणतो नेहमी, this is a y, this is a y. So this weight there mg, and you know this angle theta, so therefore this becomes mg cos theta, this component mg sin theta, okay, sin theta. This is a normal reaction. Remember, if suppose there is a force which pulls it, that force suppose F here, and so opposite to direction of displacement or motion there is a frictional force which is nothing but mu k into r. So let us apply work energy theorem for this particular case. बघा आता इथे काय करू शकतो आपण, the forces which are parallel to direction of motion आधी ते मार्क करायचे. बघा डिस्प्लेसमेंट इकडे, the force is F, this force F is our interest force F, this mg sin theta and mu kr. So all these forces contribute for the yes work done. बघा मागच्या केसमध्ये mg हे वर्क डन मध्ये कॉन्ट्रीब्यूट करत होतं because it is has a 90 degree with displacement. You know that why it is not contributing, okay, so cos 90 becomes 0, and again it is perpendicular to displacement. But in this case force F, which is a category of applied force, mg sin theta, which is a category of weight component, and frictional force mu k r, these are, remember, forces which contributes to the work done, okay, which contributes to the work done. Remaining mg cos theta r is no use. Actually use is there. Use is like this. You can calculate value of r here, summation applying, yes, summation fy is equal to 0 you can apply there. So r minus it gives mg cos theta is equal to 0. So therefore r equal to mg cos, okay, cos theta, that gives a value of r. Now applying a work energy theorem to this total, so that's why we can write like this, W net is equal to a delta ke, okay, delta ke. So we can consider of applied force F into displacement. I am taking this positive because applied force is in upward direction, displacement is in upward direction. So applied force and displacement in the same direction, work done will be positive. Then what about mg sin theta? Let us write a force mg sin theta into displacement. Okay, what about this? मी आता काय सांगितलं तुम्हाला, if body moving upward, work done is negative. If body coming downward, work done is positive. So is body moving upward or downward? Yes, upward. That's why it is negative. There is no any doubt. And for frictional, there is no any doubt. Mu k r into yes. So this is a left hand side part of the work energy theorem. So how to apply it? Remember this. For applied force, for weight component, and for friction, deal like separately. So there is no yes will be issue about the sign conventions. So here 1 by 2, whatever its mass, final velocity square minus initial velocity square. So this completes this total equation, work energy theorem for this particular block. So W net, remember W net is very important here, not a work done here. Net work done is equal to change in kinetic energy, not a single work done, or work done by applied force is not equal to change in kinetic energy, or work done by frictional force is not equal to change in kinetic energy. Work done by mg sin theta, weight component, is not equal to change in kinetic energy. Work done by net force, or we can say net work done, is equal to always a change in kinetic energy. And that is nothing but called work energy principle or work energy theorem. In number of applications we can apply this work energy theorem instead of applying a second law of motion. In case of बघा आपण भिंतीवरती जर खेळा मारत असू तर आपला एक रेजिस्टिंग फोर्स भिंतीकडनं येईल. And if you apply work energy at that point, what happens there? The forces in the direction of motion is only resisting force, that is a frictional force. In that case, we can take that frictional force minus Ef into a displacement. जेवढा तो नेल आत जाईल, that is a displacement. आपण बघणार आहोत याला डिटेलमध्ये, पण एक एक्झाम्पल बघा, minus F into S is equal to 1/2 half mv F square minus vi square. So that is atomically adjusted. आणि जेव्हा बघा Vf, if Vf is greater than Vi, so this at that time work done will be, yes, there is an increase in kinetic energy, nothing but increase in kinetic energy. And remember, this is a positive work. And when Vf is less than Vi, okay, if body moving and stops because of, so there is a change in decrease in kinetic energy, and that is given by a negative work done. So this is how to apply a work energy theorem for this block system. आपण वेगवेगळ्या सिच्युएशन मध्ये हा work energy theorem you can apply everywhere. Okay, so this is a replacement of Newton's second law of motion or extension of that particular kinetics, whatever you have studied in that. So concludely, what we have studied, a work done by all forces acting up on the particle is equal to change in kinetic energy, and our sign conventions you have to deal with carefully. If displacement and force are opposite to each other, the work done will be negative, you know that. And if force and displacement are in the same direction, work done will be positive in that case. And for frictional resisting force, remember always a work done is negative. It is either moving upward, downward, rightward, leftward, anywhere. It is always opposes the work done, and therefore work done by frictional force always taken negative. Okay, so let us stop here, and yes, in next lecture we have to apply this work energy theorem in real time problems and subsequent MCQs.